We're also going to need to discover sources of human capital, physical capital, and financial capital. On the human capital side, we're going to need scientists who can do the research, come up with the ideas, and present us with the technological options. We're also going to need entrepreneurs who can found the organizations that are going to get us started on the transition. We're going to need professional managers who can take over those organizations at some point, scale them, and grow them. And we're going to need financial types who can essentially do the task of deciding for us which projects are going to get funded and which projects are not going to get funded. I think we've got a great sampling of that kind of human capital on our panel. We have two panelists who will speak primarily from the investing side. We've got Scott Brown, who is CEO and co-founder of New Energy Capital, which is a New England-based venture capital company with investments throughout the energy sector, particularly in biofuels, renewable power generation, and cogeneration. And Scott's been involved in the energy business for a long time. We also have David Wells, who is at the venture capital firm Kleiner, Perkins, Caulfield, and Byers. David focuses on green tech investment at this firm, and he's got investing and operating experience in a wide range of energy technologies, and he couples that with great knowledge of markets. Our third panelist is Sean Casten, who is a Thayer graduate. He will be speaking more from his experiences in working with and running energy-related companies. He's currently the president and CEO of Recycled Energy, which recycles industrial waste energy. And Sean's been deeply involved in the energy industry for a long time as well, including a stint with Arthur D. Little. Our last panelist is Lee, of course, who's not only co-chair of this panel, but has been the overall organizer of the entire symposium and done a yeoman's job on that. He's one of the key kinds of individuals that we're going to need to complete this transition because he's really one of these environmental entrepreneurial scientists. He's professor of engineering at Thayer as well as an adjunct professor of biology at the college. He's an expert on the use of plant biomass for the production of energy, co-founder and chief scientific officer of Muskoma Corporation, a cellulosic ethanol startup which, if you believe our local newspaper, is creating a shortage not of cellulose, but of office space in the Upper Valley. And my son pointed out to me in this month's Wired magazine, Lee had a great spread in Wired magazine, which I thought actually did him a lot of justice. The structure here is going to be 8 to 10 minutes per participant of a presentation. We'll try to hold questions, I think, to the end. We'll have about 40 minutes of hopefully good questions and answers at the end. So let me start with David. You're going to need to use that.
Hi, everybody. I just want to speak a little bit about what the energy resource and emissions world looks like to us, and our outlook on how we can help solve problems while also fulfilling our traditional role of making money for our limited partners. The risk we run in today's environment is that when you carry a really big hammer, everything looks like a nail. And we're in a situation now where there's huge opportunity created by the pressures that we've been discussing here today. And everything looks like an opportunity to us. So we've been spending a lot of time and energy trying to sort through this green tech landscape to understand what is and isn't an opportunity, and where the scale of venture investment can really make a difference. So the first point is that energy is really very, very big. Used to be on the screen behind me, is the US energy flows, 98 quadrillion BTUs, and you can think about that in terms of maybe your electric kettles or electric heaters, or how many BTUs are in those. 98 quadrillion BTUs is an unimaginable amount of energy. And one of the things to notice on this flow chart, which is made by John Ziagos at Lawrence Livermore National Laboratory, are the gray bits. The gray bits are the amount of primary energy that we throw away. We bought that energy. We bought that fuel. We dug it out of the ground. We bought it from the Saudis. We burned that coal. and then we just throw it away. We're throwing away more than half of it. That's a really big opportunity. So continuing on with the theme of how big energy is, Earth's primary energy consumption today is running at about 13 trillion watts. So to, again, try and make that into a human number, we have 6.5 billion people on the planet. If you put a 1,000-watt hairdryer in each hand of every single one of those people and turned them all on, that is 13 trillion watts. And the picture is more distorted than that because Americans are holding the equivalent of about 5 hairdryers in each hand. And the rest of the world, a lot of them have got 1 hairdryer for every 5th person, and they all wish they had a hairdryer in each hand, and they're all trying to get them. So we're headed for 25 terawatts, 28 terawatts, more. Big challenge, big opportunity. And then the other way in which energy is really, really big is money. For instance, Platts, which is a global provider of energy and metals information, does a study on the top 250 energy firms every year. And the last year for which I saw the numbers, they came up with revenues of around $4 trillion for that top 250 firms. And they admitted that they were leaving out some big firms in developing countries. So it's a really, really big market as well as a big energy target. So if you start looking at the technology ecosystem of that 13 terawatts, what you see is that energy technologies have evolved from pre-industrial origins. If you look at motive power, we went from fire to steam engines to understanding the laws of thermodynamics to building internal combustion engines to building gas turbines. If you look at electricity, we're still basically doing the same thing we were 150 years ago, fooling around with magnets and metals and rotational motion. These things have evolved incrementally a step at a time. And that's where all the effort has been going to a large degree, is doing that incrementing. And what's often been missing in technology innovation is drawing a bigger box around the challenges. Doing a first principles analysis of the boundaries of what is possible rather than incrementing from what exists today. So that's something that we have done, is we have tried to understand across a wide range of technologies what the chemical, physical, thermodynamic, and quantum mechanical limits of that technology are. And then we look for people who are taking that viewpoint of technologies and taking a clean sheet to achieving technologies that lie at those boundaries. A good example is light bulbs. I mean, right now, there are very big companies that generate a lot of revenue selling really, really well-evolved, very, very good versions of rotten technology, just terrible technology. The boundary of turning electricity into light is 300 lumens a watt. The light bulb you buy down at the shop is 13 lumens a watt. That's a disgrace. But it's a great piece of technology. We can make them in huge volumes, we can ship them worldwide, and everyone's got the same bulb to plug them into. You could just go, yeah, that's good. So that's a huge opportunity when you have a piece of technology that's used worldwide like that, where you have so much room between the status quo of the technology and the theoretical boundaries of that service that we wish we had, which is light. And many people will say, yeah, we've got LEDs, and it's true that there are LEDs in the lab at 150 lumens a watt. But there are still a lot of challenges before we can use those devices for general illumination.